All right, so this begins lecture 10 on Frenet curves in Rn. Roughly speaking, we're following Wolfgang Kuhnel's chapter 2 of Differential Geometry, Curves, Surfaces, and Manifolds. A delightful book. Okay, fine, you could skip to lecture 11 without much of a loss of story for R3, but I hope you won't, because I think it's an informative experience to see a little bit about the theory of curves in Rn. Let's see here. So when we think about a curve in Rn, right, you have, I guess you can picture it something like this. So here's your x1, here's your x2, and here's your x3, 4, xn. Okay, and so at each point along the curve, right, you want to do something like fit one vector, well, it's not just one. I mean, you got, how many vectors do you got to fit there? You got to fit a frame of, you need n of these at each point, right? And somehow that's going to define a Frenet frame along a curve in Rn. So first of all, I should talk a little bit more about what is a frame in Rn. Very similar to the frames we've talked about in R3, of course. First of all, you need as many vector fields as you got dimensions. So we need E1 through En vector fields in Rn. We need these vector fields to be orthonormal. So we need Ei dot Ej to be Kronecker delta Ij, like so. There, we can again use an attitude matrix to talk about various aspects of the frame. So Ei, and I still haven't talked about orientation for frames in 3 dimensions, but I will do that hopefully in the next lecture. Sorry for the delay on that. Aij Uj be the attitude matrix, and through essentially the same argument we gave before, you could show that A transpose A. Oh, I forget. Maybe I already did frames in Rn. I can't even remember at this point, sadly enough. But this makes A, of course, an element of n by n orthogonal matrix, right? And so you either have the determinant of A is equal to 1, or you have the determinant of A is equal to -1. These are said to be positively oriented, right? The frame is positively oriented. Here the frame would be negatively oriented. All right. Now in 3 dimensions we could capture positive and negative orientation in terms of the third member of the frame being the cross product of the first 2. I do think I talked about that before, but we haven't come back to it. We will again soon. Okay, so that defines a frame in Rn, all right? Well, the interesting thing is, of course, in Rn, we don't have the cross product anymore, right? Cross product special to 3 dimensions. So the question is, how do you, we use the cross product to get that third thing. We use the cross product to get the binormal. And so there has to be some generalization of that story here for Rn, and the generalization necessarily involves some linear algebra. All right, so here's the central algebraic, I guess you could call it backbone. I don't know what it is. What do you want to call it? The algebraic backbone to this whole thing is the following. So if you're given an orthonormal set of, say, codimension 1, and in other words, you have E1, E2, En minus 1, so you have almost enough vector fields to get Rn, but not quite enough. Then you can construct the last one, the remaining one, En, as follows. You can just write, it's the sum, let's see here, I'm going to write it slightly different than I wrote in my notes, just to get to the point here. It's really the sum, j equals 1 to n, right, of the determinant of E1, E2. Now obviously what am I doing here? I am, goodness, I guess you could say I'm if you think about this in terms of transposes, then these are just rows. These are just the determinant of the attitude matrix. Well, we don't have an attitude matrix yet because we don't have a frame yet. But the first n-1 rows written as columns in the attitude matrix, if you prefer, or the coordinate vectors of e1 through en-1 in the Cartesian coordinate system. Whatever floats your boat. Anyway, you can find a way to interpret this which makes sense. Think about it for a bit. So you have this determinant of e1 through en-1, and then you stick uj in the last spot, and then you make it a vector like this. This, of course, is just the natural generalization of the cross product formula mnemonic we give in Calc 3, where we put the unit vectors in the top row and we put the components in the remaining two rows, right? And then we, if you really take a look at it, it's that formula. Okay, so my claim is that this then makes E1 through En, in fact, a positively oriented frame. So it's a claim. With En so constructed, E1 En forms a positively oriented frame. All right. Now, roughly the calculations I'm about to show you are reminiscent of problem 129 or 130 from my spring 2015 linear algebra course. If you had the joy of taking that course, you may recall these as being some of the more difficult homework problems. But, you know, once you see past some things, it's not too bad. For example, En, first of all, we should establish orthogonality of En with Ei for, say, I between 1 and n-1. All right. So En dot Ei then is equal to, what is it? Well, it's, you know, this expression. All right. So sum j equals 1 to n, determinant E1, E2, En-1, uj, and then what we got? We've got uj dot ei using a property of cross product, dot products rather, to bring it inside the summation, right? But recall that aij is equal to ei dot uj, right? So this is nothing more than aji, right? So if you bring that inside the determinant using multilinearity of the determinant in the last slot, linearity rather in the last column of the determinant, you have yourself E1, E2, En-1, right? And then, oh, I forgot to bring, I meant to bring the sum inside. I'm using multilinearity, sorry. I'll get it right eventually. Sum j equals 1 to n of a, oh, I'm sorry, this was aij, right? So aij, uj, aha, but this is precisely ei. All right, by definition of the attitude matrix, or to be more precise, it's the column vector corresponding to ei in the standard basis, all right? And so then, but ei is also in this list, so you have repeated columns, therefore the determinant 0. Bam. So there you have definitely a proof that at a minimum, En is an element of the orthogonal complement of the given n-1 orthonormal vectors. All right, it's definitely in the perp. But it's more than that. You can show, you can demonstrate that En dot En is in fact equal to 1. Right? And that, sorry, let me write just a little bit higher. You can demonstrate that En dot En is equal to 1 and the determinant of E1 dot En is equal to 1. So it is in fact a positive frame. And so in this way, we can calculate the nth vector from the given n-1 orthonormal vectors. So this is important because the assumption for what we're about to, well, let me just get to it. The reason this is important is because the definition of a Frenet curve is as follows. Alright. So I'm going to go ahead and use my notes some here as to avoid too much writing. Oh no. Hey, let me call you back. Okay, bye. Sorry about that. Wandering Bailu approaches, how should we proceed? Alright, there we go. Okay, so... Oh, I don't like the way that shows up on here. I guess I'll write it out. Sorry guys. Let me zoom back out. So 2, what is the definition of a Frenet curve? A Frenet curve is one which basically permits us to construct a Frenet frame around it. Frame on it in a natural way. So what's a Frenet curve? We have a couple assumptions. We have to have alpha smooth curve from I to Rn, as usual. Smooth parametrized curve. And I think we assume, arc length, with arc length parameterization. Of course, as usual, you could drop that and suffer speed factors here and there. So this is in some sense a convenience, arc length parameterization. And you need that alpha prime, and so forth and so on until you get to the n-1th derivative of the curve. These are linearly independent. And so what that really means is, evaluate at t and I, and we have linear independence at each, or I should say in each tangent space at alpha of t of Rn, okay? So they give you this linearly independent set of n vectors. Of course, if they're linearly independent, they're non-zero. Alright. What that means, by the way, of course, is that each point we could run the Gram-Schmidt algorithm on these at each time t. Time. Oh, man. Well, think t equals to s. Sorry. Notation, whatever. We can run Gram-Schmidt on these at each arc length. At each point on the curve anyway, and that Gram-Schmidt will give us a set of n-1 orthonormal vectors. Then we go back to page 1 and we use the determinant, the generalized n-1 area cross product, if you like, to generate that last nth orthonormal vector to give us a honest-to-goodness frame in Rn. But we say, so that's a Frenet curve. So I just told you how we could take these velocities, acceleration, so forth, and generate a frame. And we call that a Frenet frame if the following holds. We say E1, E2, En is a Frenet frame if the following three conditions are met. So 1, you need that E1, E2 En are orthonormal and positively oriented. All right. Of course, that's at each point along the curve. 2, for each k, 1, 2, n minus 1, we have the span of the first k of these frames. All right, it's fitting. It fits with the span of the first k minus k derivatives. I feel like, oh, not k minus 1. There's the first k of these fits with the first k derivatives. All right. Now, that's exactly how Gram-Schmidt works. Gram-Schmidt does it. You would do Gram-Schmidt on these. The vectors it produces, E1 through Ek, will fit this spanning condition nicely. So that's not a burden to the Gram-Schmidt algorithm. 3, alpha k, kth derivative dot Ek is I think that I got a greater than sign in the notes. I do think it means is equal to 0 for. Oh no, greater than 0. I'm an idiot. The reason these have to be greater than 0 is these are exactly the curvatures. You say curvatures, yes, curvatures with an s. K equals 1 to n minus 1. All right. So in particular, we define the ith curvature for such a Frenet frame to be equal to, well, okay, this is not the curvature, but it's related to the curvature. The curvature is actually EI prime. So I'm getting ahead of the story a little bit here. But I think that positivity is necessary in order to keep this quantity greater than or equal to 0 for you know, I equals to 1 to n minus 2. All right, it's going to take me forever and a day to write all this stuff out, so I'm actually going to cease and desist the writing here momentarily. Just one more thing. Let's see here. So just to give an example, I should give at least one example in here. Oh goodness gracious! So alpha of t. Ooh. I guess if I was to start with the twisted quartic, so something like here's an R4, t squared, t cubed, t to the 4th. I'm pretty sure, I am not 100% sure this is Frenet curve. I have hope. Let's see here. So, of course, this is not arc length parametrized, right? So, oh man. Oh, what a drag. So to arc length parameterize this thing. Oh, it's unpleasant, isn't it? Well, let's look at a second here. Alpha prime T1. Of course, I really mean, goodness gracious. U1 plus 2t U2 plus 3t squared U3 plus 4t cubed U to the U4, and then your acceleration. So yeah, like 2U2 plus 6t U3 12t squared U4 alpha prime of t 6U3 plus 24t U4. So I think, although I'm not 100% sure, if I was to, well, soon we'll have, a little bit later in the presentation, Kunal actually does give some comments about the non-arc length parameterized curve. So this example really belongs there. It's just I can't stand to arc length parameterize this thing. It's just too awful. But you can see that, you know, modulo the pesky arc length thing, which is done so in part so that the curvatures are defined uniquely in terms of the arc length parameterization. These will give you linearly independent though, because it's like this has a U1 component. This has no U1 component. This has no U2 component. So it's going to be like a triangular matrix. This would be an example of a Frenet curve once you fixed the speed problem. So I guess back in n equals 3, it's probably worth a comment. In n equals 3, if you think back to n equals 3, this Frenet curve, well, we looked at nonstop regular curves, right? So regular curves means alpha prime was not equal to 0, right? And alpha prime prime was what? Was not equal to 0 as well. That's nonlinear, right? And you can also see that these were not linearly dependent either. We saw that before. So basically, a nonstop. The curves we studied before were in fact Frenet curves in R3. It's just for R3, the linear independence condition basically boils down to just saying, hey, the second derivative's got to be non-zero. All right. Okay, so actually, I think my next example my next thing in my notes, which I will share with you now, is these, Frenet-Serret equations in Rn. Very, very cool. Natural generalization of what we already worked out. So here's what they look like. So as you can see, you have a Frenet curve, you have Frenet frame, the Frenet-Serret equations in Rn describe how the frame evolves in terms of the change in the frame in response to possibly non-trivial curvatures. And the n-1th one is called the torsion. Now the curvatures are all positive, but the torsion could be positive or negative. But you can find the proof of this on page 27 in Kernel. And it's similar again to the proof we gave in n equals 3 case. Now, I would point out that by theorem 3.22, if we're given an isometry f, we can push a Frenet frame, E1 through En, to another Frenet frame, f, push forward frame, f star E1 through f star En, at the transformed point, f of alpha of s naught, and that's for the transform curved by the isometry f composed with alpha. And you can calculate then that the determinant of the push forward frame, right, which would be this is the attitude of the pushed forward frame. It's going to be equal to, so basically remember the push forward of an isometry is just r times the orthogonal matrix part of it times the vector, the component, the coordinate vector for the vector. And so I get one of those on each one of the columns. Then by the concatenation proposition, I can factor the r out from linear algebra. And then product of determinants determine the product, so that pulls out the determinant of r. And so if E1 through En is a Frenet frame, that means this is positive 1. So in order for the push forward frame also to be a Frenet frame, I need that the r is in fact a rotation. I need that the determinant of r is 1. So there you go. On the other hand, if I had the determinant of r was a rotor reflection, or determinant of r was, if r was a rotor reflection, or a reflection, if you like, the determinant of r would be -1, and that would cause the torsion to actually reverse sign. One example I have this little two-dimensional example, which we did three-dimensional curves, right? But the Frenet-Serret stuff also makes sense in 2 dimensions. It probably makes sense in 1 dimension in some stupid way, but I haven't thought about that. Oh well. I should be a better mathematician. Anyway, suppose we have a Frenet frame in R2. It suffices to have a regular curve because that's it. That's the n-1th derivative, right? Okay, so if that's not equal to 0, then it's a Frenet curve. If I define E1 and E2 by some functions a and b of arc length, right, you can see that these will be orthonormal because this dot that gives me minus ab plus ab when you take the dot product. And I also, of course, need that a1 squared plus b, a squared plus b squared is 1 for the magnitude of E1 and the magnitude of E2 to be 1. Now the curvature is the magnitude of E1 prime, all right, and I've also assumed that E1 is set up to be, so basically here Where's E1 coming from? E1 is coming from what it almost always comes from in these constructions. I just set up E1 to be the unit tangent, all right? And it's arc length parameterized, so it's just the tangent. It's the velocity of the curve is E1. Then E2 I got to construct by some other means. Now here I just used my go-to method, which is switch the components and put a minus in for 2 dimensions. Technically that just corresponds to geometrically, if E1 is here, you rotate 90 degrees. And then you got a perpendicular vector, right? That's actually what this is. That's the 2-dimensional cross product. Take your vector, rotate 90 degrees. Check it out. Other vector, which is perpendicular to given vector. I say cross product with quotes. So anyway, the curvature then is the square root of a prime squared plus b prime squared, because e1 prime, of course, is, differentiate this, I get a1 prime u1 plus b prime u2. The magnitude of that is this. But then if you think about a specific curve, for example, this circle, then the velocity is this, and so e1 prime is that, and that implies that the curvature is 1 over the radius, which of course, perhaps, we did see that before in the 3-dimensional case, but here's a 2-dimensional calculation that shows you again the curvature of a circle is the reciprocal of the radius. But notice that this is a 2-dimensional example, which is not something we had before. There's another theorem which is of interest, and this is the sort of reverse theorem, which is actually, I think, even more interesting than the things we've done. This basically says that if you're given potential curvature functions, right? So you suppose you're given these functions ki, which are non-negative, and then you're given an n minus 1th one, which I guess could be, I lost track of my, so the n up 1 through n minus 2 have to be non-negative. For example, n equals 3, you get one non-negative one, which is we call the usual curvature, and then the n minus 1th one, the second curvature, is actually what we call the torsion for R3, right? Also for Rn, we call the last curvature the torsion. If you're in R5, you've got 4 curvatures. The first 3 curvatures are non-negative. Did I say R4? If I'm in R4, I have 3 curvatures. The first 2 are non-negative, the third one is the torsion. All right, if I'm in R5, I've got 4 curvatures. The first 3 are non-negative, the fourth is the torsion. It could be positive or negative, or 0. Okay, so if you're given these potential curvature functions, a point, and also a frame, all right, then there exists a unique Frenet curve alpha for which it matches up the point and matches up the frame as its Frenet frame, and more than that, it reproduces the given functions as curvatures. This is very cool, because this means that if I give you a set of functions that are of the right type, then you can find me a curve which takes those functions as its curvature. So this can be found, the proof of it can be found basically on page 28 of Kuhnel, and ultimately it rests on some existence and uniqueness theorem from differential equations, which we have not proved. So here's another example. So this is kind of the, let's see here, what is the point of this example? Let me remind myself. I say we want to find, we found in example 3.2.6 that the circle has constant curvature, which is reciprocal to its radius. I say this example follows, the example which follows investigates the reverse question. Find the arc length parameterized curve R2 for which the curvature is constant. Aha! So basically I'm trying to flesh out the previous theorem for the specific case of constant curvature in the plane. So basically what I've faced with is a set of differential equations to solve. But these are, as much as these are similar differential equations you see in differential equations, they're a little bit sneakier, see, because these differential equations we're looking at here, e1 prime equals kappa e2 and e2 prime equals kappa e1, you should notice that these are differential equations between vectors of functions. This is actually two ODEs, and this is actually 2 more ODEs. There's actually 4 ordinary differential equations with constant coefficients sitting here. But they're simple enough you can see that if I substitute the first equation into the second, you'll get e1 prime prime minus kappa e1 kappa squared E1, but once I would typically think about that as E1 prime prime plus kappa squared E1 equal to 0, and then perhaps if I wrote it y prime prime plus kappa squared y equals to 0, then this kind of thing we definitely solve in differential equations, right? But you can solve the same here for vectors. You just have to, instead of putting constant numbers, you put constant 2 vectors, and that gives you a solution. And then E2 can be found from differentiating and dividing by the curvature. And then you can find the curve itself from integrating E1, which, remember, E1 was the velocity curve. So I get alpha of s is equal to alpha naught, some constant, 1 over kappa this, minus 1 over kappa that. But then if you look at you can identify alpha naught as the center of the circle, right? So alpha of s minus alpha of naught, the magnitude of that will be 1 over kappa times the magnitude of this vector, but that vector is nothing more than the negative of E2, which we know has length 1. And so there you go, 1 over the curvature is equal to r, just as we'd hoped. So there's actually an example of how you can give, say, a constant curvature and solve the Frenet-Serret equations using methods of differential equations. I would say that generally speaking, that's that's a hard pill to swallow. Here's a trickier example, which I think to really finish well would take a while. So here's another one in 4 dimensions. Suppose you have constant curvatures, k1, k2, and torsion tau. Alright, I'll use tau for k3, kappa 3 rather. So you face these Frenet-Serret equations. They're constant coefficients, ODEs. E1, E2, E3, E4 is each a set of 4 functions of time. So don't be fooled, this is actually a sneaky notation for 16 constant coefficient ODEs. But you know what? It is a constant coefficient linear ODE, so that means the matrix exponential solves the system. All you got to do then is find there's something really special about these. I mean, yeah, it's 16, but it's really 4. These are very special differential equations. I think that if you develop the full theory of how to solve them, it would be very satisfying and special. But anyway, not the point here. If you calculate the determinant of this, x minus that gives you what's called the characteristic equation here, and you work it out. Eventually you get that the solutions come in complex pairs, like plus or minus I gamma, plus or minus I beta, and that makes sense because the trace of m is 0. That's obvious from this, and that's consistent with my claim. 2 pairs of complex zeros. The plus and minus terms cancel, right? And also the product of the eigenvalues should give you back the determinant. That also squares with this result. Anyway, so generally speaking, oops, I'm out of frame. Sorry about that. So I was just saying we get a pair of complex zeros, and anyway, eventually you get to some solution like this: cosine gamma s, sine gamma s, cosine beta s, sine beta s. These are 4-dimensional vectors of constants. That would be the velocity to this curve in 4 dimensions, which has constant curvature and constant torsion. You can look at page 32 of Kuhnel for more explicit formulas, some rather something. I mean, they're really neat formulas. And he explains that this actually gives you curves which wind around a particular torus in 4-dimensional space. Very neat. Anyway, there is more, of course, to read in Kuhnel about total curvature and other things, but we'll get back to that material later as we study the problem of the the Gauss-Bonnet theorem, which of course is one of the central results of this course. Anyway, that concludes my brief tour through curves in n dimensions. I'm sure that there's much more to learn here. But I wanted to make you aware of it, and I want to invite you to read Kuhnel's book if you want to see more. That's not quite the direction of this course, but I think it's important to touch on it. Thanks.